Hi everyone, today I'm going to explain two interesting control surface configurations used in aircraft design, the Ruddervator and the CANARD. These are alternatives to traditional tail and control setups, and they play unique roles in how an aircraft moves and stays stable in flight. We'll start with the basics of flight control systems, then explore what Ruddervators and CANARDs are, how they work, and why designers use them. Before we dive in, let's quickly go over how airplanes are controlled. Aircraft movement is controlled in three axes: pitch, roll, and yaw. Pitch is the up and down motion of the nose. Roll is the tilting of the wings. Yaw is the side-to-side movement of the nose. To control these movements, planes use three primary control surfaces: elevators to control pitch, ailerons to control roll, rudder to control yaw. There are also secondary control surfaces, like flaps and trim tabs, which help improve performance but don't control the aircraft's orientation directly. Now, let's look at how Ruddervators combine some of these primary functions. Ruddervators are found on aircraft that use a V-tail configuration. Instead of having a separate vertical and horizontal tail, the V-tail uses two slanted surfaces. Each of these surfaces is a Ruddervator, a combination of a rudder and an elevator. So, how do they work? When both Ruddervators move up or down together, they act like elevators, controlling the pitch of the aircraft. When they move in opposite directions, one up, one down, they act like a rudder, controlling yaw. This system replaces two separate control surfaces with just two, making the design lighter and more aerodynamically efficient. But it's also more complex to manage because the control inputs must be mixed mechanically or electronically. That's usually done using a control mixer, which ensures the surfaces respond correctly to pilot inputs. Here are how the Ruddervator in action from interior view and exterior view. How they move. When the pilot wants to raise the nose, pitch up, both Ruddervators move down. When the pilot wants to lower the nose, pitch down, both Ruddervators move up. To turn right, yaw right, the right Ruddervator moves down and the left one moves up. To turn left, yaw left, the left Ruddervator moves down and the right one moves up. A special system called a mixer combines the pilot's pitch and yaw inputs and moves the Ruddervators in the right way. Let's break down the advantages and disadvantages of using Ruddervators. Advantages: reduce drag. By eliminating the vertical and horizontal stabilizers and combining them into a V-tail, Ruddervators help streamline the aircraft. Weight savings: fewer surfaces and simpler structure can mean a lighter tail section. Sleeker design: this can be useful in aircraft where speed and efficiency are important, like light sport aircraft or early jet trainers. Disadvantages: complex control mixing. Because Ruddervators serve two functions, the control system needs to translate pitch and yaw commands into combined surface movement. This adds mechanical or software complexity. Reduced directional stability. The lack of a dedicated vertical stabilizer can affect yaw stability, especially in crosswinds. Challenging maintenance. It can be more difficult to diagnose control issues or adjust the system correctly, increasing the chance of errors if not done carefully. Next, let's talk about CANARDs. A CANARD is a small wing located at the front of an aircraft, ahead of the main wing. It's like having a mini elevator at the nose. CANARDs control pitch, just like elevators do, but they can also provide lift. In fact, in some aircraft designs, the CANARD replaces the horizontal tail entirely. There are two main types of CANARDs: control CANARDs, which are movable and directly controlled by the pilot. Fixed CANARDs, which are designed to always generate a certain amount of lift. In aircraft with CANARDs, the main wing is usually located farther back than in traditional designs. This changes the center of gravity and the aerodynamic balance of the plane. Let's take a closer look at how CANARDs work. A CANARD is a small wing-like surface placed near the front of an aircraft, ahead of the main wings. It's used to control the aircraft's pitch, just like a traditional tail-mounted elevator. But instead of being at the back, it's at the front. When a pilot pulls back on the control stick, the CANARD surface deflects upward, increasing its lift. Since it's positioned in front of the center of gravity, this causes the nose of the aircraft to rise, just like when elevators at the back push the tail down. In many cases, the CANARD is actively controlled, meaning it moves in response to the pilot's input. In some designs, it's fixed but carefully angled to always provide a small upward lift, which helps balance the aircraft. One of the key benefits of this setup is stall prevention. The CANARD typically stalls before the main wing. When that happens, it loses lift, which naturally drops the nose, helping the plane recover before the main wing loses lift. This makes it much harder for the aircraft to enter an unrecoverable stall. CANARDs can also improve maneuverability, especially in fighter jets, because they give extra pitch control at high speeds or during tight turns. In short, CANARDs generate lift, enhance pitch control, and can improve both safety and agility, depending on how they're designed. Now, let's look at CANARDs. Advantages: lift contribution. Unlike a horizontal stabilizer that typically creates downward force, a canard can generate lift, improving efficiency. Improved stall behavior. Since the canard stalls first, it naturally lowers the nose, helping the aircraft recover before the main wing stalls. Better pitch control authority, especially at low speeds or during high angle of attack maneuvers. Disadvantages: interference with airflow. Canards can disrupt airflow to the main wing, especially at high angles of attack, which may reduce overall lift or create turbulence. Design complexity. Balancing lift and stability becomes more challenging, especially in tailless or unstable configurations. Visibility and cockpit placement issues. In some configurations, canards can interfere with pilot sightlines or restrict instrument placement. So, both ruddervators and canards are part of the primary control system because they directly control the aircraft's attitude, especially pitch and yaw. Ruddervators control pitch and yaw by combining two traditional surfaces into one. Canards control pitch and can also improve lift and prevent stalls. Each system reflects a different design philosophy. V-tails and ruddervators are about simplifying and reducing drag. Canards are about adding control and improving lift efficiency. These systems show how creative aircraft engineers can be when optimizing for speed, stability, or maneuverability. Primary control systems: attitude, operation, and maintenance. In common aircraft designs, primary control systems, including elevators, ailerons, and rudders, directly affect the aircraft's attitude, pitch, roll, and yaw. Ruddervators, as we've seen, combine the functions of elevators and rudders in V-tail designs, controlling both pitch and yaw. From an operational perspective, these surfaces are essential for safe maneuvering, takeoff, and landing. In maintenance, primary controls require regular inspection for mechanical wear, correct control linkage tension, and surface integrity. Any failure could lead to a loss of control, so their maintenance is critical. Ruddervators demand extra care due to their dual functionality and the complexity of their mixing mechanisms. Calibration and proper operation checks are essential to ensure that the surface responds correctly to pitch and yaw inputs. Secondary control systems, like trim tabs, flaps, and slats, don't change the aircraft's orientation directly but influence how efficiently or safely it can maintain or change its attitude. For example, canards in some aircraft act like stabilizers or flaps, especially in fixed or lifting canard configurations. In these cases, they help delay stalls and improve pitch control during low-speed operations, such as takeoff or landing. Operationally, these surfaces assist pilots by reducing workload and improving control in various flight phases. Maintenance-wise, secondary systems are inspected for proper alignment, actuation, and aerodynamic cleanliness, since performance can degrade if these surfaces malfunction. To wrap up, ruddervators are combination surfaces found on V-tail aircraft. Canards are forward-mounted mini-wings that help control pitch and lift. Both are used in primary flight control systems, and both affect the attitude of an aircraft. That's how it's oriented in space. Thanks for watching. I hope this helped you understand how ruddervators and canards work and why they're used in aircraft design. That's all from both of us, sincerely Farish and Amar from 2AEM10.